Hello, welcome back. This is Calculus by Dr. Oz. So today we're given two infinite series with a parameter p in it, and we're going to try to apply tests that we learned so far to check for the convergency of these infinite series depending on the values of p. So you can apply any of the tests, any of the applicable tests to the given series. But this is sort of like your assessment to check which test is more applicable to the given series. So we have two infinite series provided to us. So let's get started.
All right, let's start with part A. In this problem, as I told you earlier, no test is being told to be used. So for that reason, we're going to sort of like try to check what we can use. We can try integral test because I have the impression that I can integrate ln x over x to the power of p by using integration by parts. So maybe we should go in that direction. Okay. So why don't we start using the integral test? In fact, but I want to make sure that the integral test is applicable for this infinite series. So all I'm going to do is I'm going to go ahead and then write down an equals fn, which is ln n over n to the p, and then here f of x is ln x over x to the p, and here x's are greater than or equal to 2 because the sum here starts from 2. Okay, so I have three conditions to check. F being positive, F being continuous, F being decreasing. Okay, so let's check. For x is greater than or equal to 2, is f of x positive? Okay, well, ln 1 is always 0, and starting from 1 all the way to infinity, ln x is always positive, and the bottom is as well positive, no matter what p is, by the way. P is a power. It could be negative or positive as long as n, or as long as here x is positive. So we are safe. So the bottom is always positive. So you can go ahead and conclude that f of x is positive. And continuity, well, ln x is continuous as long as you are talking about positive x's, because ln 0 is undefined, but ln x is always continuous starting from 0. But in our case, x is greater than or equal to 2, so we're safe saying that ln x is a continuous function itself. And no matter what p is, as long as x is not 0, and as long as x is not 0, we're not dividing by 0, so we should be safe calling that x to the p is continuous. So since the top and the bottom are continuous themselves, right? So the ratio is going to be, or the quotient is going to be continuous. Again, as long as the bottom is not 0, which we avoided it because x is greater than or equal to 2. So I can say f of x is continuous on x greater than or equal to 2. Same thing here, x greater than or equal to 2. Okay. And the third condition is f decreasing. So is f decreasing? So to check that, remember we always rely on to the first derivative test. We have to find the first derivative of the function. All right, let's look at f prime. We're going to use the quotient rule for finding the derivative here. So the derivative of ln x is 1 over x times the bottom minus ln x times the derivative of the bottom. So use the power rule for that, p times x to the power of p minus 1. Okay, all divided by the square of the bottom. Okay, let's simplify this. So 1 over x is x to the minus 1. So x to the minus 1 times x to the p is x to the minus 1 plus p, right? So we just add the exponents, right? And then I have minus p ln x, x to the power of p minus 1, and x to the p squared is x to the 2p. All right, so in fact, I can write this as like p minus 1 here. So why don't we just write that? It's the same thing. So that I can pull out x to the p minus 1 at the top. So 1 minus p ln x, all divided by x to the 2p. Okay? And here, remember that x's are supposed to be greater than or equal to 2. So once we decide the sign of f prime, we're going to consider x as greater than or equal to 2. As well, we're talking about positive values of p. So p is positive. All right. So going back here, if p is positive and x is positive, starting from ln2, in fact, ln3 is bigger than 1. If p is 1, we're safe. If p is greater than 1, we're still safe. Well, however, it depends on what p is, if p is in between 0 and 1, because we want this part to be negative. So if you provide me exactly what p is, let's say p equals 1/3, I can choose x starting from a number, not necessarily 2, but maybe 4, 5, maybe. I can still guarantee that this term is negative, because I don't need to worry about these two. These are going to be positive no matter what p is. Okay, so again, as long as p is positive, I can play with this x here, the lower bound of x, so that I can make this term negative. So f prime becomes negative, and going back to here, I can conclude that f is a decreasing function. Okay, and once you have all three conditions met, then you can go ahead and then look at this integration here. In this case, we're going to look at the integral from 2 to infinity. But the lower limit is not really important. I'm not sure if you get this part, because even if I start this this integral from 4, that's okay as long as this is convergent. I'm just going to add 2 more terms in the sum, because it just tells me that this sum starting from 4 an is convergent. Okay, so what is the difference between this sum and this sum? Just 2 terms, and those are finite numbers. If this sum is convergent, and adding 2 more terms to that is okay. So in other words, the lower limit is not playing an important role in this analysis, just so you know. But obviously you have to make sure that all 3 conditions are met for x is greater than or equal to that lower bound. But again, one more time, I'm telling you, you can play with the lower bound as long as these 3 conditions are satisfied. Because p is a parameter here, I don't know exactly what p is, but if you provide me p, I can prove all 3 conditions to be satisfied, and I can go ahead and look at this improper integral with a lower limit that could be 4, 5, 6, 7, 10, some finite number. It doesn't matter. Okay, so let's start.